All right, we just got done watching the video on force diagrams. We're going to draw a couple of these here. This first page, the first 18, you're not going to be responsible for drawing these. This is just a quick review to make sure that you understand what's going on. So if we have a diagram like this one right here, we only have one force that's pulling to the right. So this object would accelerate to the right with a net force of 4 newtons. The next one, number 2, we have 4 newtons to the right and we have 8 newtons to the left. So the net force, the sum of these two, would yield a 4 Newton force to the left. So this object would accelerate to the left with 4 newtons worth of force. Number three, the net force between these two is 0 newtons. Now we can't say that this object would be stationary because we don't know what the velocity is. Since the net force is 0, all we can say is it's going to continue doing whatever it's doing. Number 4, we look at the net force between these two. We have a total of 5 newtons that's going to act to the right. We have number 5, there's only one force and it's acting upwards. So you'd have some 7 up. 7 newtons upwards. The next one, number 6, you have 10 newtons up, 4 newtons down. So your net force here would be 6 newtons upwards. Number 10, if we add up the two forces on the right side, you have 9 newtons worth of force. 3 newtons is acting against that. So your sum or your net force, since they're acting in the opposite directions, you go 9 minus 3, you've got 6 newtons worth of force. It's going to move this box to the right. You have number 8, you have the two forces left and right. They're canceling each other out. So it's not going to move left or right, but we do have a 4 Newton force that's acting downwards. So the net force here would be 4 newtons down. Number 9, we have 6 newtons acting towards the, let's call it the southeast. There's no other forces acting on it, so our net force would be 6 newtons to the southeast. Number 10, there are no numbers here, but where would this go if we were going to draw this out? Well, this would be like the vector diagrams that we had been working on. We have 2 vectors working concurrently on the box. So what we could do is we could draw the first one here, and then the second one, you draw it right after it. So our resultant vector would look something like this. So it would go to the lower right. We have the next one, again, working with those vector diagrams that we had. We know that we have one force that's to the right, one force that's downwards. So the resultant force would look like this. Number 12, this one, we have a down and right. So where would it go? We have that. We have number 13. We have one vector that's upwards. We have one vector that's to the right. So our resultant will be to the upper right. Number 14, you have one vector that's pointing down to the right. The next one is pointing up to the right. So this is just going to go straight across for our resultant. Number 15, they're both in the same direction, so what would happen is we would just add those 2 vectors up like this. Number 16, we have one vector that's pointing upwards, one that's right, so our resultant would look like this. So you can see where all of our vector work is going to come into play because we're going to have a lot of vector diagrams in the dynamics portion of the class. This one right here, if we add them all up, we get a net force of 0. This isn't going to move anywhere. And then our last one here that we're going to go over, and this is just, I know I'm going through them kind of quick. It's because we've already talked about vectors, and it's just an idea of what we're looking at. All right, so let's make sure that we know our definitions, our terms, before we start actually drawing out some of these free body diagrams. All right, so first off, our free body diagrams, we're always going to have just some box. It doesn't matter if it's a boat or person or a cat. It doesn't matter. We're always going to draw them out with a box, all right? And Then we're going to draw any interaction with some other object in terms of arrows or vectors. So if this boat has the earth acting on it, the earth is going to pull down on the boat. The boat, as it presses into the water is going to press backwards up onto it. That's what we call the normal force. Okay, so you should have an idea when we're talking about these free body diagrams. We try to look at all of the different forces that are going to be acting on this object. All right, so the first force that we're going to take a look at here in terms of definitions is going to be gravitational force. The gravitational force, if we wanted to calculate what your body weight is, you would take your mass, all right? So if you had a mass of 100 kilograms, you'd be about 220 pounds roughly. And what we would do is we'd multiply that by the pull of gravity, 9.8 meters per second squared. So this person, if you weighed 220 pounds, you would, and let's round this off to make it easy, you have 10 meters per second squared. This person would weigh 1,000 newtons, and I don't know why I had to do that. That'd be 980. I feel like my son trying to grab a calculator to do something like that. Anyways, we're going to diagram this now. How do you draw a free body diagram depicting gravity? So here we have a person, right? It doesn't matter what we're looking at. We're always going to draw it with a box. Gravity is center seeking. So the earth is going to pull downwards on the center of this mass, this person, okay, with a force of, I don't care which one we pick, all right? So we're going to have 980 newtons. And what we would do is we would label this with an F. And then myself, I always put down, since this is talking about weight, I'm going to put FW for this. All right, now, that person is going to be standing on the earth, all right? And they're not going to be sinking into mud. They're not going to be falling through water. So if we're going to diagram this same object, the same person right here, this one, if we diagram this, now what's another force that is going to act on this person? Well, this person, if they're, as I said, if they're standing on the ground and they're not sinking into the ground, there's going to be a support force that the ground is going to apply onto the person's feet. Now, what we do here is we would draw that force to be equal and opposite. I'm trying to draw the two vectors to be equal and opposite. So this right here, we'd call that, oops, let me start with my force. We'd call that the normal force. Oftentimes, I refer to this simply as the support force, okay? And since the support force, this person isn't sinking into the ground, they're not being projected up into the air, we'd say that the support force is equal to the weight of the person. That would be that 980 newtons. All right, so we have our gravitational force, we have our normal force, frictional force. This one's pretty simple. If we're looking at our frictional force, we have an object on the ground here, okay? And that object on the ground, if we have an applied force, so I'm going to put FA, all right? So a lot of times some people will put FA PP for applied force. We're not going to do that. We're just going to put down FA. So we have our applied force. Frictional forces act against this. All right, so if frictional forces are going to act against it, it's going to be in the opposite direction. So sometimes people will put down FR for resistance. Myself, it's just kind of whichever day that we're talking about. Sometimes I put FF. All right, now another thing that we need to take into consideration, if we're looking at all of the forces that are acting on this object right now, we also have, remember, you have the weight of this object pressing down onto the earth, and then we have this support force that's acting upwards on it. All right. Now, we know that the blue vectors, the weight and the normal force, they're equal to each other. When we're looking at that applied force, in this case, let me make this to where they're both equal and opposite. Another way that we could write this out in terms of friction, we learned before that different surfaces in contact with each other, they're going to have different coefficients of friction, different grippiness. If you take a book and rub it across the tabletop and it's two smooth surfaces, there's not going to be a lot of friction. But if you take two pieces of sandpaper and try to rub them past each other, there's going to be a greater amount of friction, a greater amount of grippiness. That's the mu, or coefficient of friction. So we have our applied force now. All right, so here's the FA right here. If the applied force is where we have two objects that are sliding past each other, you should take into consideration that we know that the object is being pressed down into the earth, and the earth is interacting with all of those little, uneven surfaces of the block in this case. All right. So where does this mu, or the coefficient of friction, come into play? Well, the coefficient of friction comes into play. Now we're going to put down mu. That's the symbol for mu. The coefficient of friction is just a number times the normal force. Now, a lot of people, they'll take and put down Fn right here. Sometimes they'll put down just N. But in this case, when we're looking at this particular diagram, I know that I have an applied force acting to the right. There is a frictional force that's acting in the opposite direction with equal value. This particular situation right here, this might be like a book sitting on top of the table. Somebody's just not applying enough force to get it to move. All right, we have three types of forces. We have our push and the pull. That one's pretty simple. If you're looking at a diagram, here we have a push, all right? But we would have to make sure that that force that's coming towards it's pushing it right here. And then if you're going to have something pulling, we would want to diagram it like this, okay? Tensional forces, if we have, let's say, a chain, and then we have a box that's suspended from it, all right? Tensional forces, we have the force between the object being pulled down right here. Now, the actual surface that we're talking about is right here, and then the tension is within that chain, okay? So that would be the upward support force acting on the picture frame or box or whatever you want to call it. All right, after going through those, you should have an idea of how we're going to diagram these. Now, we're going to start out with some easy ones where you have the diagrams drawn and then you just fill in the rest of the information. And then we're going to get into ones where you have to draw this stuff out. So from here on, this is what needs to be on your piece of paper. So we've got a free body diagram here, situation A. You have 3 newtons that's acting up, 3 down. It's not going to go anywhere in terms of up or down. We have 5 newtons of friction to the left. We have 5 newtons of applied force to the right. If we're looking at the net force here, our net force is 0 newtons. We go to situation B. Situation B, if you have 3 newtons up, and that would be like a tensional force, we have 3 newtons acting downwards. It's not going to go up or down, but you do have 5 newtons to the left, and there's nothing acting towards the right. So in this case, we would have a negative 5 newtons. Why negative? Because it's pointing to the left. Letter C, I'm going to let you draw this out, and if we're comparing their values, well, it doesn't have any more up than down, so this one would be 0 newtons. The last one, You have 40 newtons acting upwards, 25 acting downwards. So if we take the sum of these, you got 40 minus 25, you've got a value of 15 newtons that's acting upwards. Our diagrams here, I'll go over 2 of them, and then you have to do 2 of them yourself. So if we have our net force of 0, that means that we have everything balanced. We have 200 newtons acting downwards, so letter B, what does the value here have to be? It has to be 200 newtons acting upwards. It's not moving anywhere, left or right, either, so if it's 50 newtons to the right, then A has to be 50 newtons to the left. I'll do one more with you, and then you have to do the other 2. Let's take, let's go with this one right here, letter D and E. Let's take a look at this. So I know that this is going to be going to the left with 60 newtons of force. Now, it doesn't say that it's going up or down, so this thing has to be 300 newtons acting downwards. Now, it says that it's 60 acting to the left. So if I added the 80 and then whatever D here is, my total would have to be 60 to the left. So D here has to be 20 newtons of force, because if I would take 80 minus 20, I'd get my 60. All right, so you have to do letter C here, and then you have to do F, G, and H. Then on the last part of this, I said that you'd have to draw some diagrams yourself. So we'll do a couple of them, and then I'm going to turn you loose, and then you have to finish the rest of them up yourself. It says a book is at rest on a tabletop. A free body diagram for this would look like what? Well, we have the desk. Okay, so here what you'd have to draw is your desk. You wouldn't really have to draw, since we're talking about a free body diagram, you wouldn't have to draw the actual desk in here, but I'm just showing you what I want you to get. So looking at the forces, we know that if a book is sitting on the desk, we'd have the weight of the book acting downwards. And then the tabletop would be supporting the book. So supporting the book, it's not moving upwards or downwards. That's your normal force. So what would the free body diagram of this look like? Well, you'd have your box, you'd have your weight of the object, and then we would say that we would have the support force that would be acting upwards on it like this. All right, so this is what you'd want to have. All right, if it helps you to draw out a diagram like I did right here, do it, but if not, you don't need to. All right, let's go to number 4. It says a girl is suspended motionless from a bar and hangs from the ceiling by 2 ropes. All right, so if we look at a picture of something like this, all right, we're describing the girl that's on this bar. Okay, so here's the ropes right there that she's holding on to. It says that we need to draw a free body diagram depicting this. All right, well, first one, that one's going to be easy. We have the weight of the girl that's going to be acting downwards, but then there's going to be some support force acting upwards on this hand, and then there's going to be some support force acting upwards on this hand. Now, you might just impulsively jump into drawing this out, and you say, okay, well, here is the weight, and then we'd have those tensional forces, and you might do something crazy like this. You can't do that, because if we did this, you have what would be significantly more force acting upwards than downwards. So this girl would be moving up, not just sitting still. All right. So what we need to do is we need to look at the length of our vector that we have drawn downwards. All right. And what I'll do is I'm going to draw 2 vectors that would be roughly 1/2 of each other. Okay. See, if I take this one and I draw another one like this, both of these put together would equal the weight the weight acting downwards. All right, so when you draw these out, you have to think about what is the magnitude of these vectors that you're drawing out. All right, we'll look at maybe one or two more, and then you have the rest of those. You got up to number 12 to do yourself. All right, so we have number 5. Number 5, it says that an egg is free falling from a nest in a tree. All right, so here, if we got the egg, that's a round egg. So here, if that's an egg that's falling from the tree. Now, we know that if something's falling, we're going to have the weight of the object. Gravity is going to be pulling this guy down. All right, now it says it's in free fall. Free fall, there is no air resistance acting on this. All right, so free fall, no air resistance. So if there is no upward force acting on this, no air resistance, you're done. That's all it is. Let me go over one last one with you here. All right, the last one, let's say that we have this squirrel that's going to be flying through the air, okay? It says that it's just going to be gliding, no flapping. That's going to be pretty easy. That's similar to number 5, but you'd have resistance. Let me pick one that, let's say number 7 here. 7, I think, would be a little more challenging for you. It says a rightward force is applied to a book in order to move it across the tabletop. Now, the first thing I'm going to do, you wouldn't have to do this, but I'm going to sketch this out so that way you can see it. You've got this book that you're pushing across the tabletop. So you know that you have an applied force, but since you have two surfaces in contact and they're going to be rubbing against each other, you're going to have some frictional force here. And it says that it's a rightward force, so I've got that right. And it says that it's a rightward acceleration. So my frictional force here, my resistance has to be less, this has to be less than the applied force. Either that or it wouldn't be moving to the right. It wouldn't be accelerating to the right. So let's draw our free body diagram for this. You have your book. We know that the weight of the book is going to be acting downwards, so I'll put this on here. We know that the table is supporting the weight of the book. That's the normal force. All right, so Fn. I know that there is an applied force that's going to be pushing the book across the tabletop. And then I know that there's going to be a frictional force that's acting against us. Now what I'm going to do is I'm going to put in here, since we know that the two surfaces in contact, there's going to be a certain level of grippiness with it. So I'm going to put down mu, that's that coefficient of friction, times, well, in order for those two surfaces to be in contact, it has to have the support force of it, okay? So this is the friction. When we're talking about this right here, this is the frictional force, the resistance acting on it, okay? So what you have to do right now to finish this up, you've got number 6, 8, 9, 10, 11, and 12 to finish up. Once you have those completed, you go ahead and take a good picture of it, submit it up to Schoology, and you're all finished. If you have some questions, make sure that you ask, and I'll do the best I can to answer them via email, or if you get into the open office hours, we can do it that way too. All right?